Hello, and welcome to ZTech's webinar on new tools for maximizing the performance of FMC and TFM inspections. My name is Michael Mussman of ZTech. I'd like to thank everyone for joining us today. As an on-demand webinar, there is no live question and answer section at the end. Instead, you can email your questions at any time to webinars@ztech.com, and we will respond directly back to you. Before we begin the webinar, I'd like to give you a quick overview of ZTech. ZTech is a global NDT leader. For over 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. ZTech's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. ZTech is a subsidiary of Roper Technologies. Let's get to today's session, which will be presented by Guy Moss. Guy has been involved in advanced UT method development and implementation, capability assessment, and software development for more than 25 years. Since 2000, Guy has held various positions at ZTech and RD Tech, including Sales Director, Product Manager, and UT Applications Manager. Guy is currently the Sales Engineer Director, UT at ZTech. With that, I'd like to now turn the webinar over to Guy.
Thank you, Michael. Hello, everybody. I'm Guy Maas, and I have the pleasure of presenting this webinar about some exciting new tools for maximizing the performance of FMC and TFM inspections with Topaz 64 and UltraVision. This is our agenda for the webinar. First of all, I will briefly review the principles of the full matrix capture data collection process and some advanced focusing techniques like TFM and STF. After that, we will look at some live UT imaging on a reference block to illustrate the benefits of FMC and advanced focusing techniques, but also the conditions required to exploit the full potential of this technology. I will then demonstrate the new acoustic field tool that we have recently introduced on our complete Topaz product family. You will see how this tool helps UT operators to optimize the coverage and the detection capability of their PAUT and TFM inspections. The last part of the webinar will address the additional benefits of recording and processing the raw FMC data. I will show results of case studies on various challenging damage mechanisms and illustrate the potential of several advanced FMC data reconstruction algorithms that are available in the newest release of our UltraVision Classic software. And finally, we will wrap up with some conclusions from the presented material. With the full matrix capture or FMC technique, the elementary A-scan signals from every transmitter-receiver pair are captured and recorded. Like the image on this slide shows, the elements of the probe are pulsed one by one, and for each pulse, the reflected signals are received on each element. At the end of the sequence, for a probe with 4 elements, a matrix of 16 A-scan signals is recorded. For a more realistic situation, a probe with 64 elements, we will have a matrix of 4,096 A-scans. From the raw A-scan signals, it is then possible to generate UT images for any given focal law in terms of aperture, angle, or focus depth, and for advanced focusing techniques through post-processing and recently also live during inspection. The most commonly used advanced focusing algorithm is the total focusing method, or TFM. This animation explains how it works. The TFM algorithm sums the elementary A-scan signals from all elements in the array to generate a frame of pixels, where each pixel is computed using a dedicated focal law. The TFM frames can be used for live interpretation, or they can be stored for each position of the probe, very similar to a dynamic merge view in regular phased array. In theory, ideal focusing is achieved in each point of the frame. I will show later that the focusing capability of the technique still depends on the acoustic wavelength and the total aperture of the array. Therefore, some conditions must be met to effectively obtain ideal focusing. The elementary A scans from the FMC data recording can also be used with an alternative processing method to generate a sectorial sweep of A scans while focusing in each point along the sound path. We will call this technique sectorial total focusing, and its physical principle is very similar to a DDF or dynamic depth focusing algorithm, applied both in transmission and in reception. Again, the operator can perform online data interpretation, or the images can be recorded during an encoded inspection sequence. The algorithm has the benefit of recording a summed A-scan signal for each angle, very similar to standard phase array, and this might facilitate its acceptance in codes and standards. Before looking at real flaws in the case studies, let me start by illustrating the benefits of advanced focusing techniques and the key parameters that allow to exploit the full potential of this new technology. I will use the well-known ASTM E2491 phase array reference block with different sets of side drilled holes, and a typical 5 MHz linear array probe with 64 elements coupled to an L-wave wedge. We are looking at ultrasonic images of a set of 1 mm diameter side drilled holes located on a vertical line. Two channels are shown simultaneously on the Topaz 64. On the left side of the screen, we have a high-resolution TFM frame, 512 by 512 pixels, generated with the complete 64-element aperture of the probe. The calculator in UV Touch shows the coverage of the frame relative to the specimen and makes it easy to set and adjust the parameters of the frame. On the right side of the screen, we have a standard phase array sector scan showing angles between 20 and 70 degree L waves and a resolution of 0.5 degrees. Again, the complete 64 element aperture is used. The standard phase array channel is focused in projection mode, just in front of the wedge. In the starting position, we can see that the TFM algorithm, in combination with the large aperture of the probe, allows for ideal focusing on all reflectors. At this specific probe position, the standard phase array sector scan is also well focused on all reflectors and shows a similar, nearly perfect image. When we start moving the probe by roughly 10 millimeters in one direction or the other, we can observe that the image provided by the standard phase array technique shows defocusing on most of the reflectors, simply because the sound field is focused elsewhere. On the other hand, for the TFM technique, nearly ideal focusing is conserved over a large range of probe positions. This clearly illustrates the capability of TFM to focus in the complete region of interest and not only on a predefined locus. I have now replaced the TFM channel on the left side of the screen by an STF channel with the same angle sweep as the standard phase array channel. And we perform the same test again, starting from the ideal position for the standard phase array and moving the probe away from that position. And very similar to the live TFM technique, the live sectorial total focusing technique conserves nearly ideal focusing over a large range of probe positions. As previously mentioned, the active aperture of the probe is a key parameter for the focusing capability. This slide clearly illustrates the influence of this active aperture on the TFM imaging. Live TFM images of the same set of side drilled holes were recorded with different apertures. From left to right, 64, 32, and 16 elements of the probes were used to generate the TFM frames. The images show that a large aperture is required to fully benefit from the focusing power of the TFM algorithm, and the same can be demonstrated for the STF. Indeed, even when advanced focusing algorithms are applied, the focusing capability is still limited to the near field of the probe, and this near field can be increased by selecting a probe with a larger active surface or a probe with a higher frequency. Let us now look at the influence of the TFM frame resolution on the detection capability and the reliability of the inspection. We start from the same setup that we used a few minutes ago, showing a TFM frame of 512 by 512 pixels. We can see the TFM frame on the left side of the screen and the amplitude depth curve on the right side of the screen. This curve is like the A-scan signal of a virtual 0-degree probe in each horizontal position of the TFM frame. The different echoes represent the responses from the side-drilled holes, and we can see a regular sensitivity distribution. If we go into the TFM calculator, we can see how to define and adjust the frame by defining the frame start and frame extent horizontally and vertically. The TFM calculator in UltraVision Touch also includes an easy tool to help the operator select an adequate and code-compliant frame resolution. The depth and width of the individual pixels is shown in wavelength units. The user interface also shows the calculated value of the amplitude fidelity. This parameter represents the maximum possible amplitude error for a TFM frame according to the Nyquist or sampling theorem. For the 512 by 512 frame, we can see that the pixel size is a tenth of a wavelength, and the amplitude fidelity is less than 0.5 dB. This is compliant with the new mandatory Appendix 11 of ASME Code Section 5 about FMC, requiring an amplitude fidelity of 2 dB or less. So even if the Topaz 64 can support 1024 by 1024 frames, this very high resolution is not required for this specific configuration. It will, however, be necessary for shear wave inspections on thicker components. But let us now change the frame resolution to 128 by 128. Immediately, the TFM calculator gives a warning sign. Indeed, we can see that the pixel size is now as large as 4/10 of a wavelength, and the amplitude fidelity exceeds the code-compliant threshold of 2 dB. If we keep the low resolution anyway, we can see that the TFM image has a very different aspect now. It looks pixelized. Also, the A-scan signal on the right shows irregular amplitudes for the echoes from the reflectors. And when moving the probe very slightly, actually less than a millimeter, we can observe random and important variations in the echo amplitudes, as if some reflectors are disappearing and reappearing. The pixelite aspect of the TFM frame can be improved by applying the smoothing feature available in UltraVision Touch, but the important amplitude variations remain. Obviously, an actual inspection with these parameter settings would be very unreliable and could leave real flaws undetected. And this is exactly why codes have introduced the amplitude fidelity parameter. Let us now look at some exciting new features in our equipment and software. The Acoustic Field tool is now available as a standard feature in the onboard software of the complete Topaz family of integrated phase array systems, and in the UV Touch software for PC. Over the next few minutes, I will illustrate how this tool can help you maximize coverage and performance of phased array and TFM inspections with your Topaz unit. The Acoustic Field tool is integrated in the UltraVision Touch calculator on all Topaz units. For a standard phase array configuration, the acoustic field can be calculated and visualized for a single law or for a subset of laws in the azimuthal sweep. The operator can select the number of beams to be visualized on the screen. The calculation is quite fast, typically a few seconds,
but it is not implemented as a mandatory step that can potentially slow down the inspection workflow. Compared to the more common ray tracing image, the acoustic field tool gives a much better assessment of effective coverage and detection capability. In this example, after increasing the probe aperture, the acoustic field shows better focusing in the region of interest, and the live sector scan image shows a drastic improvement of the resolution and signal-to-noise ratio on the reflectors. The acoustic beams can also be shown skipping off the far surface for a more intuitive coverage assessment of weld inspection with shear waves. In addition to azimuthal sweeps, the tool also supports field calculation for linear and compound sweeps. TFM is a promising new inspection technique, and phased array operators look for guidance on how to fully exploit its capability. For a given probe and wedge connected to the Topaz unit, the acoustic field can be calculated and visualized for different TFM wave modes. The operator just needs to select the construction path and then proceed with the calculation. This example shows a TFM setup for weld inspection. Comparing the acoustic field of the T-T and the TT-TT wave modes clearly illustrates the higher sensitivity of the reflected wave mode for defects in the weld bevel.
The embedded Ultravision Touch software on Topaz 32 and Topaz 64 supports setup of dual matrix array probes for inspection of austenitic components and welds. And the acoustic field tool is also available for such probe configurations, both in phased array and in TFM mode. This example shows the calculator setup for our standard large 1.5 MHz DMA probe on a typical dissimilar metal weld configuration with a thickness of 40 mm. The acoustic field is calculated for 7 beams in the azimuthal sweep from 30 to 85 degree L waves. The image clearly shows that the near side of the weld is adequately covered from the considered probe location. But the second scan line will be required to make sure that the far side of the weld and the buttering are covered in the focal region of the beams, and the acoustic field tool helps the operator optimize the scan plan. This slide is a short summary of the features of our new onboard acoustic field tool. It can be applied for both flat and cylindrical components and welds. As shown earlier, 1D linear and 2D matrix arrays are supported for both pulse echo and pitch and catch configurations. The acoustic field for standard phase array beams, as well as the various reconstruction modes of a TFM configuration, can be rapidly calculated and visualized. And finally, the user interface can provide the value of the maximum acoustic field amplitude for the sweep of beams or for each individual beam. The Topaz 64 phase array system has the capability to record raw FMC data in addition to live TFM frames. After recording, the Ultravision Classic software can be used to reconstruct various data groups from the raw FMC data, including standard phase array signals, TFM frames, or sectorial total focusing images. The FMC snapshot tool allows to collect a complete TFM frame at one or more discrete probe positions, typically where flaws have been detected. In our first example, I will use the same setup used earlier in this webinar with the 5 MHz linear array probe and the L-wave wedge on the ASTM reference block. The acquisition setup includes a live TFM frame and a standard phased array channel focusing at 50 mm half path. First, the operator verifies that the unit is in snapshot mode and then goes to the inspection tab. Upon hitting the FMC snapshot button, a complete set of 4096 elementary A scans is collected, and all channels can be saved together on an external hard disk connected to the Topaz 64. Upon opening the data file in Ultravision Classic, the two live channels are again visualized. The reconstruction of the FMC data is performed in the familiar advanced calculator interface. The operator can adjust the TFM frame parameters, for example the frame size and resolution, and then process the data reconstruction. UltraVision Classic can rapidly reconstruct TFM frames up to at least 16 megapixels. We can now compare the data groups. Although the live TFM frame on the left satisfies the 2 dB amplitude fidelity rule, we can see that the reconstructed frames of 1 megapixels in the middle and 16 megapixels on the right offer better resolution on the reflectors. It is also possible to reconstruct standard phase array data for any given focal law and for sectorial total focusing, both with very fine angular increments. Here we show the reconstructed sectorial total focusing channel with an angular increment of 0.2 degrees. In addition to the excellent focusing and the very fine resolution on the sector scan view, this algorithm generates an A-scan signal for each angle, just like standard phased array. The next FMC snapshot was taken on a specimen with an EDM notch, using the same 5 MHz probe and L-wave wedge. The typical L-L wave mode was already processed, and we are now processing the same FMC raw data using the LL-L reconstruction mode. The L-L wave mode on the left shows the back wall of the specimen, the tip and the corner trap of the notch, and allows for very accurate through-wall sizing. For this type of planar flaw, perpendicular to the ID surface, the LL-L wave mode on the right provides additional information from the surface of the flaw. The Topaz 64 also allows to record FMC data in full data mode. This means that a complete set of elementary A-scans is stored at each probe position in an encoded sequence. Ideally, this requires an automated scanning mechanism to control the movement. We will now process data from a carbon steel plate weld, where FMC frames were taken every millimeter, together with a live phase array channel. The data reconstruction process is the same as shown before, first adjusting the TFM frame size to 512 by 512 to obtain code-compliant amplitude fidelity. Obviously, the reconstruction operation takes more time than for a single snapshot. The reconstructed TFM data group has exactly the same format as the results from a volumetric merge operation. It is easy to use the projection gates to isolate and visualize individual flaws, like the near-surface toe crack with well-resolved corner and tip signals. We can also observe the capability of the TFM technique to provide excellent resolution for imaging the cluster of porosity. Let us now take a deeper dive into some data reconstruction algorithms for raw FMC data. I will not go too much into mathematical details, but just try to point out some key differences. The most commonly used TFM reconstruction algorithm is based on a DAS or delay and sum approach. It basically applies appropriate delays to the individual pulsar receiver A-scans and sums them afterwards. A similar approach is used for the regular STF reconstruction algorithm. In the newest release of our UltraVision Classic software, we have introduced several alternative algorithms. The TFM DMAS, or delay multiply and sum algorithm, sums the delayed pulsar receiver A-scans multiplied by each other. This process reduces the well-known TFM artifacts that are in fact partially constructive interferences, often occurring in the presence of large refractors like the back wall of a component. The TFM envelope algorithm processes analytic signals obtained from the pulsar receiver A-scans using the Hilbert transform. The envelope is obtained from the magnitude of the summed analytic signals. The resulting images look like phased array signals with a smoothing filter applied. And finally, TFM with phase coherence factor reduces the side lobes of the imaging. This slide shows the new user interface for the data reconstruction process in UltraVision Classic, with the previously discussed options. It's important to mention that the new tools can be combined and can also be applied for reconstruction with the sectorial total focusing algorithm. The names of the process data groups will automatically adapt to mention the applied algorithms and resolution. Let's now look into some case studies to illustrate the potential of the advanced data reconstruction algorithms that I've just presented. First, let us go back to the raw data from the FMC snapshot we took earlier on the aluminum specimen with the machined notch. This slide shows images of the notch in the L-L wave mode from live TFM and from 5 different reconstruction algorithms. The live TFM in the upper left corner is a 256 by 256 frame, which is code compliant but close to the 2 dB amplitude fidelity threshold. All the reconstructed data are 1 megapixel frames. When zooming in on the notch, we can observe that the TFM envelope image in the upper right corner is smoother than the regular TFM and may simplify data interpretation. But more obvious is that the DMAS and PCF algorithms strongly reduce the artifacts from the corner track. In this example, the best image in the lower right corner is provided by combining DMAS and envelope processing. The height and even the width of the machined notch can be accurately measured. And here we can see the same algorithms applied for the LL-L reconstruction of the raw FMC data of the machined notch. We previously saw that for planar flaws perpendicular to the ID surface, the LL-L wave mode provides additional information from the surface of the flaw. When looking at the images generated by the different algorithms, we can again observe that DMAS and PCF in combination with the envelope eliminate a large part of the TFM artifacts and provide a clearer image of the flaw face. In our next example, we will look at the imaging of small, low reflectivity targets close to large geometrical reflectors. For this purpose, we took an aluminum calibration block with 2 side-drilled holes and added multiple small holes drilled from the ID. The end of these regular drilled holes is conical, and therefore they are poor reflectors for essentially straight beam UT. A standard LM5 MHz probe was used in direct contact with the specimen. This slide shows images of the region of interest in the L-L wave mode from live TFM and the 5 reconstruction algorithms that we saw in the previous example. The gain setting was adjusted to bring the calibration side-drilled holes to roughly 80% screen height. Typically, when looking at challenging damage mechanisms with low reflectivity, like for instance HTHA or creep, operators need to apply increased gain settings. In our example, when we increase the soft gain on all images, the typical TFM artifacts from geometrical reflectors like the back wall produce strong background signals on the images from live TFM and the regular reconstructed TFM. The envelope adds efficient smoothing to the image, but does not reduce the artifacts. Obviously, these background signals will jeopardize reliable detection of small, low reflectivity targets. On the other hand, on the 3 images below, we can see that the DMAS and the PCF strongly reduce the artifacts and thus improve the signal-to-noise ratio of the global image. When the envelope is applied together with each of those 2 algorithms, we obtain smoothened images. The last part of this webinar addresses the inspection of austenitic material. The anisotropic coarse-grained structure of stainless steel and dissimilar metal welds typically results in a strange behavior of the ultrasonic beam when propagating through the material. And this finally results in very challenging conditions for phased array UT inspections, like high attenuation and high ultrasonic noise caused by individual large grains. The following case studies are an update on the experimental work that is done at ZTEC to investigate and document the potential of advanced focusing techniques for the inspection of austenitic components. In the first example, we consider a wrought stainless steel plate weld, 1-inch thick with a V-bevel, and we will look at inspection data from a 2.25 MHz dual matrix array on a TRL wedge. The considered flaw is a 5 mm high toe crack, but inspected from the opposite surface. And let's start looking at the flaw from the near side of the weld, so inspection through fine-grained base material. This slide shows the images from the reconstructed standard phased array sector scan in the top left corner, together with TFM L-L images from different reconstruction algorithms. Since the phase array channel is well focused on the crack, the advanced focusing algorithms don't provide a lot of extra focusing capability or resolution. But we can confirm the typical behavior of each algorithm. The TFM envelope shows a smoother image, while PCF and DMAS show far less intensity for the mode-converted signal and an improvement of the signal-to-noise ratio by roughly 12 dB compared to regular TFM. On the next slide, we still look at the crack from the near side of the weld and compare the most common TFM wave modes, all reconstructed using DMAS and envelope. And we can observe that for dislocation of the flaw on the near side, all reconstruction modes, including both L waves and shear waves, can somehow detect the crack. The direct L-L and T-T modes provide the best imaging for this far surface connected flaw. Now let's move on to the configuration with the same flaw, but inspected from the far side of the weld through coarse grain austenitic weld material. These are the images from the reconstructed standard phase array sector scan in the top left corner and the TFM L-L reconstructions with various algorithms. Just like the standard phase array TRL, the TFM L-L wave mode allows for reliable detection of the crack through the coarse grain weld material. The PCF and DMAS algorithms show an important improvement of the signal-to-noise ratio compared to the standard phase array and the regular TFM. But we can also observe a tendency to filter out the weak tip signal from the crack. Let us then look at the various TFM modes again. For the flaw on the far side of the weld, we can observe that the reconstruction modes, including only L waves, detect the crack, whereas the reconstruction modes that include at least one shear wave path cannot detect the crack. This last example clearly illustrates the benefits of recording the raw FMC data. By doing so, all basic information is available during data analysis, and the advantages of each wave mode and reconstruction algorithm can be fully exploited. Even if FMC raw data saving on a complete weld is still a laborious and time-consuming process, taking FMC snapshots or short scans in flawed or suspicious regions can be a valuable compromise. The last case study of this webinar is about dissimilar metal weld inspection. These welds typically join two or more different materials and mostly involve Inconel alloys. The image on my slide shows a typical weld configuration. Dissimilar metal welds are very challenging configurations for phase array UT examination due to the propagation issues in austenitic structures, the presence of multiple acoustic interfaces, and sometimes the complex geometry, including nozzles and tapers. Effective inspection techniques for these dissimilar metal welds are typically based on low-frequency DMA probes, generating L waves for better propagation in the coarse grain austenitic material. In our case study, we used an Aperture specimen with a wall thickness of 1.2 inches or 30 millimeters. It contains a large, branched ID surface breaking crack. The objective of our trials was to explore the potential of advanced focusing techniques for flaw characterization and sizing, using a large aperture DMA probe at 1.5 MHz. Both transmitter and receiver arrays have a 10 by 6 element configuration. The image on this slide shows the acoustic beam for standard phased array UT focused near the ID surface. We recorded raw FMC data together with the standard phased array UT channel set up according to existing best practice, with L-wave beams from 35 to 70 degrees. The full aperture of the probe was used for the two techniques. The merged view of the standard phased array technique is shown at the top of the slide. The corner trap is very well detected because the lower angles of the sector scan are typically focused near the ID. The upper part of the crack is visible, but the image is incomplete for this very high crack and would normally require a rescan, including higher angles for through-wall sizing. The image at the bottom of the slide is regular TFM L-L in a 256 by 256 frame, processed from the recorded FMC data. For this low-frequency probe, this is more than sufficient to obtain good amplitude fidelity. The image of the corner trap is almost identical, but we get a complete image of the upper part of the crack and some of the other facets, very similar to the crack morphology shown at the right of the slide. My next slide shows the reconstructions with the TFM envelope at the bottom and the TFM demassen envelope at the top. Both images clearly show the crack signals, and we can again observe an improvement of the signal-to-noise ratio for the demass reconstruction. And finally, we performed the reconstruction of the LL-L wave mode for the same advanced algorithms. For this branched crack, the LL-L mode clearly confirms ID connection and some through-wall extent of the flaw with a high signal-to-noise ratio. On the other hand, the higher parts of the flaw are not really detected. Once again, this shows that the use of multiple techniques is very valuable for characterization of complex flaws. From the information and the various case studies presented in this webinar, we can draw the following conclusions. Advanced focusing techniques are a valuable tool in the phased array toolkit. They can improve the resolution of flaw images and increase the inspection coverage with focused ultrasound. Active aperture and frame resolution are key parameters and must be carefully selected to exploit the full potential of advanced focusing techniques. Selection of appropriate probes in terms of frequency and wave mode remains a mandatory requirement for successful inspections. The acoustic field tool on the Topaz family of portable phased array units facilitates optimization of coverage and detection capability for phased array and TFM inspections. When raw FMC data have been collected, the reconstruction of different wave modes with advanced processing algorithms in UltraVision Classic can improve detection capability on challenging reflectors. In addition to industrially proven phased array and TOFT, Zetec's Topaz 64 offers fast, high-resolution live TFM and raw FMC data saving in a single, fully integrated portable unit. Thank you for your attention.
On behalf of everyone at Zetec, thank you again for attending this webinar. If you are interested in learning more about our solution or have additional questions, please email us at webinars@zetec.com. To learn more about Zetec, visit our website or follow us on social media. This concludes our webinar. Thank you and have a great day.